Hi everyone, welcome to my talk. So today I'm going to present about fast identity online with anonymous credentials, FIDO-AC. I'm Wei-Zhu from CISPA, and this is a joint work with Gunnar and Lucjan, also from CISPA, as well as Michal and Dali from Macquarie University. So to build some motivation and context, in digital authentication, we would like the user to present some kind of proof of identity or credential before the relay party or server will serve their resources. So traditionally, user would maybe provide the proof of passwords. However, we will see the trend that we will want something more of a passwordless authentications. So in this passwordless authentication space, we have FIDO standard. That is the most prominent example. And here, user will have to prove the knowledge of secret key that he have correspond to the public key. And how it roughly works is that the user will just use the secret key to sign the challenge provided by the relying party. Furthermore, relying party might also want to verify a little bit more, such as the attribute of the user. For example, the relying party would want to verify the user to be over the age of 18, for example, before serving some kind of a age-restricted resources. So user would source the certified attribute from some kind of a e-passport or e-ID that the attribute is already be certified for the users. So user could try to just present the raw passport data to the relying party so that the relying party could check the date of birth and grant the access to the resources. However, just providing the entire passport is not that great because it doesn't really satisfy the data minimization principles. Because in the process of showing the age or the date of birth, you also show your photo, your passport number, and so on. So we would like to have some kind of selective disclosure so that we only disclose the age of birth. So to summarize, we have the following challenge. We would like to combine the password authentication standard FIDO with some kind of attributes. And in the process, the attribute that we source our source from, we need the selective disclosure. And on top of that, we need the entire solution to be efficient, compatible with existing standard, and deployable in practice. So FIDO-AC is this. So what is FIDO-AC? So here we can see that on the right-hand side here is just a standard FIDO2 protocol. And on top of giving a FIDO assertions, we also just append a FIDO-AC extension data. So on the left is our FIDO-AC components where we try to source our AC data from. And this component allows us to do that. So in principle, we have three design elements. The first one is certified attributes. In our instantiations, we chose iCal ePassport as our certified attribute source. Then we also, because of our iCal eID selection, we also need some kind of a mediator that allows us to efficiently verify it. And as a side effect, mediator can also be used to generically interface with different eID frameworks. After we have our anonymous credential data, we would need it to be bound to FIDO2 protocol, so we need a FIDO2 extensions element as well. So why iCal eID? Well, it has been deployed over 140 countries, and it has been bootstrapped so that we know that a lot of users is probably going to have them, and is sort of a reliable source for our certificate attribute up to the trust from the government that issue them. So how the anonymous credential would look like? Here, the relying party could just perform passive authentication over the passport, which verify the attribute have the corresponding correct certificates. On top of that, we also need a chip authentication, which verify the liveness of the passport data, so that the user will need to process the passport at the time of verification instead of just presenting the static data from their passport. However, asking the relying party to do it violate the user linkability because of the static public key present in our passport, as well as violates attribute privacy in the sense that the relying party see more attributes than he need to enforce his policy. So before we move on, I would like to briefly talk about zero-knowledge proof. So in essence, zero-knowledge proof allows us to prove over some statements such that verifier will learn nothing more about the statement that is being proved. All right, so with zero-knowledge proof, we could ask the user to locally verify the privacy authentication of the passport as well as the chip authentication of the passport and present the generalized proof to the relying party. However, it's not efficient in practice because of the cryptographic choice made by the passport standard, and it's not that compatible with our generalized proof systems. And on top of that, the chip authentication's transcript is simulatable, so if you present it to the third party, then it's sort of deniable. You can deny that the interaction did take place. So that doesn't work this way. So to solve this, we introduce mediator. Mediator will perform both the passive authentication as well as chip authentications. And we also would like the mediator to not learn about the server policy as well as EID attribute because they are not necessary to check the authenticity of the passport. And on top of that, it kind of serves as a generic solution to our different EID frameworks. So to give more details, what the mediator will do is that mediator will verify both the PA and CA for our passport, and then it will extract the attribute digest from our passport without seeing the raw attributes. Then the user will supply the randomness so that the mediator cannot downgrade the user unlinkability. Then the mediator also sign over the FIDO server challenge because we would like that the user cannot just repeat the same mediator signature for different FIDO challenge sessions. All right, so the relying party server will just need to verify the signature of the mediator, then extract the randomized attribute digest, and then pass it as input to our generalized proof verifications to verify over the proof that the user sent over. So what the user will prove is that in the randomized attribute digest, he knows the pre-image for it, which is the attribute digest as well as the randomness used to randomize it. Then, on top of that, he supplied the pre-image for our attribute digest, which means that he supplied the attribute raw string. Then, it is some form of an attribute raw string, and then if you pass over this raw string, you obtain the attribute that you want based on the attribute that you're interested in. And then when you try to pass it over to the policy certification circuit, then it will return true, which means that the user did process the correct attribute for our policy. Okay, so this is our anonymous credential. Then, how do we bind this anonymous credential data we have to the FIDO protocol? Well, in the FIDO standard, there is some specification over some extensions, but it's not supported by the client that we use, the browser clients. So we cannot really just do that. So to be deployable in practice, we chose to append the relying party challenge with our anonymous credential data. Or to be more specific, the FIDO challenge will be appended with the digest of our anonymous credentials data, and we empirically tested it by appending about 256 bit more data, and the token that we tested, the FIDO tokens, generally support this 256 bits extension. So to summarize, we obtain our FIDO-AC as shown in the diagram. We analyze our FIDO-AC scheme by providing security proof to our PA1 models. So first, we introduce password authentications with attribute models that is based on Hanzlik SP23 models, PA models. But since we chose account EID as our source, we need a mediator to be efficient. So we introduce further augmented our PA1 model with mediator, and we call it the PA1 model. So on top of the standard FIDO security, impersonation security, as well as unlinkability, because of the attribute extensions, we further have 3 additional security notions. That is attribute unforgeability, origin privacy. Origin privacy states that mediator cannot learn about the origin of the user origin of the website the user is trying to access. Then, finally, we have attribute privacy such that mediator doesn't learn about the user attributes. The part where the relying party doesn't learn more than the policy trying to check is captured in the unlinkability definition as well. Well, in the case that we don't have a trusted mediator third party, we also investigate if we try to combine mediator and verifier and mediator and prover. So in the case of mediator with verifier, which basically means that the relay party check everything, here we still can kind of get unlinkability only if we have some form of confidentiality TEE. Then we combine mediator with prover, which is to say that the user will prove the mediator will be instantiated in the user device. What it means is that we will still get unlinkability, but to obtain attribute unforgeability, we need some form of a TE support. Or in particular, we need a key attestations for our S-specific mediator. Here, we instantiate our prototype with implementations. Here, we have implemented three things. First, we have Android mobile apps, which do the e-passport interactions. Then, we implemented local mediators backed by Android key attestations. And then we have the group setting zero-knowledge proof system using Rust artwork libraries. For our FIDO-AC server, we have it to do the transfer state of our group 16 zero-knowledge proof systems. And then we also have it host our JavaScript FIDO-AC.js that bridges communication between FIDO-AC mobile apps and reliant party logics. For our reliant party servers, it performs the standard FIDO verifications, but with the augmented FIDO challenge state. And it runs the Dockerized FIDO-AC extension verifications. So this is our performance data. And to read a EID, it takes about 1 second, but when it is read, it can be cached. To perform a liveness check, which is to say to perform both the PA and CAs, it takes about 750 milliseconds. Then to ask it to have the user to prove the zero-knowledgely the certification of the attributes. In our mobile Pixel 6 Pro Android system, it takes about 3 seconds. But if the attribute is the common attribute that the user could anticipate, then we could pre-process this proof offline. Then the server only need to do about 8 milliseconds of extra work to prove zero-knowledge verifications. And this is our implementation demo. Don't think it can be played, so. But I guess basically the demo is also available at our GitHub, so we could see over there. So we have our FIDO-AC frameworks. It combines FIDO, EID, and zero-knowledge proof to provide FIDO-AC, and it's practical and privacy preserving. And we have our proof of implementations as well as our demo video available on GitHub. So any questions?
Great, let's thank the speaker.